Okay, so now let's assume that, like we have these two piles, one with size 7, one with size 2. So now we have just 1, 1, 1 is equal to x1, and 0, 1, 0 to be equal to x2. And then we have s be equal to, if you just take the XOR of these, it'll be 1, 0, 1, which is like 5. So what we're going to do is we can do for any possible s. Take the leftmost non-zero digit in the binary representation of s. And in this case, we'll just pick this 1, so in the kind of the third position from the right. And then we want to choose some k such that the dth bit of x sub k is also non-zero. So we just want to choose like which one of these x's has a 1 in the same position, right? So in this case, it'd be x1, right? So now we say like let yk, so y1, to be equal to s and then XOR x1. And basically, we're going to change the first heap. So if you calculate this as 101 XOR 111, which equals to 0, 1, 0. So now what we're going to do is, first of all, we claim that y sub k is less than x sub k. That's because all bits to the left of d are the same. And d decreases from 1 to 0 because you decrease the value by like some 2 to the power of d. And any change will be at most like less than that, 2 to the power of d minus 1. So the first player I claim will just like take however many I guess pebbles or stones, whatever, from x1 to make it y1. So in this case, from 7 to 2. So I'll take 5 from x1. And so notice that if y is equal to s XOR x1, then t is equal to s XOR xk XOR yk is equal to s XOR xk XOR, and then itself s XOR yk, because we said s XOR xk, because we said yk too. And this is equal to 0 because it's the same thing, XOR with itself. So now we basically said like, oh, given some s that's non-zero, we can change it so that y, like the next like nim sum or XOR is equal to 0. So kind of this is how it works. This is kind of, it's not complete rigorous proof, but it's kind of like a overall thing about why it works. Yeah, and basically like a normal play strategy is kind of just like keep on making sure that you have 0, so you know like when you're ending, you win, you can pick the last one. Yeah, I mean, do you have any questions?
Yeah. Actually, is there a way to configure the pedals so that when you are giving the game to a friend, you will always win?
Yeah. So it's basically like making it so that originally it is 0, and then that means you can win. So then, actually, that's what I did with you. It was this past game. It's 5, 1, and 4. Take the nim sum of 5, 1, and 4, it becomes 0, which means that I would have won, regardless of what my partner Ian would have played. That's kind of what I did. I like whatever he played, I kind of like keep it 0 each time, kind of calculating in my head which is which. And you can do this for any number of like any like starting heap and stuff like that. And kind of just like a general thing. Nim is kind of the most basic combinatorial game. This is why it's important. There's a theorem called the Sprague-Grundy theorem that says that any combinatorial game, any game with like 2 players each like configuring a game state, and like either the ending is like whoever picks the last thing, or whoever like is left with like an empty slate, whoever that wins. So basically a 2-player combinatorial game, and the Sprague-Grundy theorem states that any of these games, whether it's like removing like stones from a pile or like something more like complicated, as long as each player has the same like ability to move, any game can be reduced to nim in some way. I thought that was pretty cool. I really like this game, and I really like combinatorial games in general. Yeah, and that's it. Thank you for watching.